Hey guys, welcome back to Math 135. Today we are starting chapter 3 on exponential and logarithm functions. And in today's class, we're only doing exponential functions. Now we're nearing the end of the semester, guys. There's only 4 more days of learning new stuff. 4 more days. And after that, we're going to focus on reviewing for the rest of the time. Now we're in chapter 3, but chapter 3 only doing 4 sections of chapter 3. Now, and also for today, so today's learning outcomes, I changed them slightly from what's written in the book, but we're still covering the same basic material. Number one, we're going to define what an exponential function is, and then two, we'll look at how to graph it, and specifically using transformations. So this is something that we learned about before, back in chapter 1, using transformations to shift a graph around, stretch it, and maybe flip it. So sorry. Number 3, how to understand the basic rules of exponents. We'll talk about that, and also how to solve simple equations with exponents. And then lastly, we'll talk about the compound interest formula, which uses exponents, and then how to define the number e and understand what that is. And by the way, just let me give you a preview. E is not a variable. It doesn't change. It's a constant, the same way that the number pi is a constant. And also similar to pi, you know how pi just goes on forever, like the digits never repeat? E is the same way. It's what we call an irrational number. All right, let's get into the topic. So number 1, define an exponential function. What is an exponential function? Well, it's simply a function of this form, f of x equal to a to the x. Notice that the x, that variable that's changing, right, that is in the exponent. Hence the name exponential function. Here the a should not be 1, because if it's 1, this is just be 1 to a power, and 1 to any power is just going to be 1, which is going to turn that thing into a constant, right? So it's not going to be 1. And also it should not be 0, because if it's 0, then this thing also is going to be a constant. It's going to be 0 to any number. It's just going to turn out to be 0. So a should not be 0, should not be 1. And right now, for now, we're just looking at the case where a is bigger than 0. Later on, we can, attack on a negative in front of it, which will be just a reflection of the exponential function. Okay, the domain, all real numbers, because you can plug in anything, any exponent, and it's going to make sense. There's no undefined parts to it. And the range is from 0 to infinity. Why 0 to infinity? Well, because if you put like if x is a big negative number, what does the negative exponent means? It means you put 1 over a to that power, right? Oh, sorry, that's not accurate. I didn't write that correctly. Let's say let's say x is some number like negative b, a negative number, right? Negative b is 1 over, a to the b then, a to the negative b, is 1 over a to the positive b, right? That's what it means to have a negative exponent. So look at this guy. It's never going to be negative, right? It's always positive regardless. That's as long as we're talking about here an a that's positive, right? The original number itself is positive. Okay, other things to know about the shape of an exponential function. If a is bigger than 1, it's going to be strictly increasing, strictly getting bigger and bigger. And if a is less than 1 but still bigger than 0, then it's going to be strictly decreasing. So we'll see each of those examples, but let me just give you a super fast preview. The increasing case looks something like this. It's got a horizontal asymptote on the left at 0, getting closer and closer to 0, and then increase super fast. It increases like exponentially. You might have heard that term before, right? Something increases exponentially. That's like one of the fastest ways of growing that you can imagine. It grows so fast. Okay, and then so if a is less than 1, then what happens? You have 1 over something that's getting bigger, right? So it's like 1 over a to the x. Think about it that way. No, I'm sorry. I'm saying that wrong. Like if you take like a fraction like a half, and we're gonna see this later, and you raise it to a power, as x gets bigger, this fraction is getting smaller, right? So it's getting closer and closer to the horizontal asymptote in that direction. And then as you're gonna cross through 0, 1, and then it's gonna explode in the opposite direction like that. Okay, but let's see how this works out in the examples. Let's try questions 1 and 2, so you'll see what I'm talking about more clearly with a simple example. And the standard, most simple example is just to use 2 as that a. A is 2. Let me copy this whole question actually with the directions. All right, so starting with number 1. Now, let's say you have no clue how to graph this. We can always resort to just plotting points, right? And so for these two, I'm just going to plot points so that you can get an idea of what's happening here, why we get what we get. Okay, so let's start with x equal to 0. That's the most obvious choice, right? This is 2 to the x. 2 to the 0, anything to the 0 power is just going to be 1. So you notice this common point of 0, 1 always occurring for these normal exponential functions. Okay, so 0, comma 1 right here. You're always going to get that point, unless you take some transformation or something. Okay, and then what about, let's do -1 and +1. So if it's -1, remember what we were saying earlier, right? What does the negative exponent means? It means you take it 1 over this base number to this 1 without the negative number, right? So what I'm saying is 2 to the -1 is 1 over 2 to the +1. And 1 over 2 to the +1, that's just 1 over 2. That's just a half. So what happened? The negative power just made it into a fraction, right? Flipped it upside down. What about 1? 2 to the 1 is just 2. Okay. And then what about -2? You know what, guys? I'm going to arrange this a little differently. Let's do it like this. We're going to continue going to the left. -1, -2, -3, and then how about 1, 2, 3 like this? Okay, so 1 we saw was 2, right? -2 would be 1 over 4, 1 over 2 to the second. -3 would be 1 over 8, 1 over 2 to the third, right? +2 would be 2 to the second, which is 4, and +3 would be 2 to the third, which is 8. So let's just plot these points and see what's going to happen, see what we're talking about here. So at 1, we're at 2. At 2, we're at 4. And at 3, we're at 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So see how fast this sky is increasing here. And this is going to increase exponentially. So at 4, it's already going to be at 16. It's going to be double that whole thing. It's doubling each interval, right? And then what about the left? It's halving each interval. So -1 is a half. -2 is a fourth. -3 is an eighth. And so you see what's happening here? It's getting closer and closer to the x-axis, but it's never going to touch. So we have this horizontal asymptote there. Sorry, that line is not straight. And then as it increases, it gets big super quickly. And this is the general shape of an exponential function for a that's bigger than 1. So the a here would be the 2, yeah? Okay, and then it says, identify the domain, range, horizontal asymptote. So let's go ahead and do that for number 1. So the domain is just everything, -infinity to +infinity. The range, it's going to be 0 to infinity. But notice this is a soft bracket because we never actually quite hit 0. And then horizontal asymptote, which we'll abbreviate HA, that's the line y equal to 0. Yeah, this line right here. Okay. So that's done. Let's try number 2 now. And we're going to approach it the same way. Start by making a table. Even though, we kind of know the shape already, but especially for this first one, let's do the table. Okay, so I got x and y, which is 1 over 2 to the x. And we're going to do the same thing. We'll start with 0. But anything to the 0 power, even if it's a fraction, pops out 1. So that's nice. We still get that 0, 1 dot, yeah? This is also going to be really helpful when you try to plot a point or try to, do a translation. You can always start with that 0, 1 and then shift it wherever it needs to go. So 0, 1 is our first point. Okay, and then let's do the same thing. Let's do -1, -2, -3. We do +1, +2, +3. Okay, 1/2 to the -1 power. That's 1/2. That's 1 over 1/2 to the 1 power. So you're basically flipping this thing upside down, right? If you have 1 over something, it reverses everything. So you're going to end up with 2. And so negative 2 is going to be 1 over 1/2 to the second power, or 1 over 1/4, which is 4. And negative 3 is going to give you 8. So it's kind of reverse of the original, right? 2 to the power or 1/2 to the power. It's reverse because it's flipped upside down. Now, what about 1? If I take 1/2 to the 1 power, that's a half. What about 1/2 to the second power? That's a fourth. 1/2 to the third power, that's an eighth. So we have the same picture as last time, just reflected actually. Right? Negative 1 is got 2. Negative 2 at 4. 5, 6, 7, 8. Negative 3 at 8. And then positive 1 at a half, positive 2 at a fourth, positive 3 at 1/8. Okay, that's not totally accurate, but you get the picture. Okay, so it's going like this. And then it starts approaching that horizontal asymptote like that. Okay, let's answer the other questions now. Domain. Still negative infinity to positive infinity. The range is still 0 to infinity, right? I can get anything as high as I want, and I can get as low as I want up to 0, but I can't quite hit 0. And then what about the horizontal asymptote? Well, it turns out it hasn't changed. It's still y equal to 0. So this is kind of, we've kind of seen another extra fact, right? The typical exponential function of the form f of x equals to a to the x. It also is going to have a horizontal asymptote at y equal to 0. And then the domain and range is always going to be that same thing. Negative infinity to positive infinity for the domain and 0 to infinity for the range. All right, in the next video, we'll talk more about graphing with translations.